All right, this is a video for our geometry class where we will be working with parallel lines and triangles, specifically working with the triangle sum theorem, but we need parallel lines to kind of get there. So we'll start with an introduction and then do a few solved examples. So many of you probably already know the sum of the angles in a triangle sum to 180 degrees. All right, so for the triangle that we see on the screen here, we can say that x plus y plus z equals 180. What you might not know is how we could prove that or justify it, okay? And it comes from parallel lines. So what I'm going to do is draw in this auxiliary line across the top of my triangle, and I'm going to make that line parallel to the base of the triangle. Okay, and my goal here is to try to justify that the sum of those three angles is 180 degrees. So the fact that we have a parallel lines gets us a lot. It gets us alternate interior angles, really. So let's look at angle x right here. We could consider this blue line to be a transversal, meaning that this angle up here is an alternate interior angle to angle x and is also equivalent in size to angle x, okay? Or has a measure of x degrees. Similarly, if we think about this purple line as being a second transversal, we can say that this is angle z, okay, or has a measure of z degrees. I'm being informal with are x, y, and z, are they the names of the angles or are the measures of the angles? I'm being a little bit informal here, and that's okay. So I hope you can see now that x plus y plus z must equal 180 because those all are adjacent angles that fall along the same line, okay? And that's a way of justifying, a way of proving that the sum of the angles in a triangle is 180 degrees. As a bit of a preview or maybe some foreshadowing, maybe you could imagine that if we didn't know these rules about parallel lines, quite possibly we then wouldn't be able to justify or know that the measure of the sum of the angles in a triangle is 180 degrees. And that gets into this idea of non-Euclidean geometry, which I hope you study at some point. That's not the focus of today's video, but as a little bit of an aside, as a tangent, non-Euclidean geometry analyzes what happens if we don't know that these lines are parallel. So anyway, now we are working in Euclidean geometry. We know that the sum of the angles in a triangle is 180 degrees, and so we can apply that and we can find some different measures. So it looks like we're looking for angles x, y, and z. I'm going to find x first. One thing that you'll find challenging in a lot of these geometry problems we're being asked to solve is when we're dealing with overlapping triangles. So we'll get there. First, just to find x, we're not dealing with overlapping triangles. We have one small triangle on the left. I hope you can see that 43 plus 59 plus x has to equal 180 degrees. So we can just take my 180, we can subtract away 43, we can also subtract away 59, and then we can get x from there. And I get x is equal to 78 degrees. Okay, and that's always a good thing to label as soon as we know what it is. So this is a 78-degree angle right there. It looks like x and y are a linear pair. So those are going to be supplementary. So next we can say that y is 180 minus the 78 that we just got. Okay, because those two angles have to sum to 180. So y is going to be 180 minus 78. And I get 102 for that. So y is 102. And so let's label that right in there as well. So this is a 102-degree angle. I'm actually going to show you a different way of getting z than you might imagine. We certainly could get z by working with this small triangle, but I referred to earlier this idea of overlapping triangles, and I wanted to show you an alternate way of getting angle z. So imagine this triangle right here, the large triangle. Okay? So let's work on finding angle Z in that triangle. So we can say that 59 degrees in the lower right plus the two angles added together in the top of that triangle plus Z has to be 180 degrees. Okay? This is a little bit more involved of a way of getting it, but it's still a way of demonstrating multiple pathways to get a solution. So we can subtract, we can take 180, we can subtract the 59, we can subtract the sum of 43 and 49, and that will leave us with Z. So let's go ahead and do that. 180 minus 59. I get Z is equal to 29 degrees. Okay, so we found the three missing angles in that particular triangle. I'm going to give you a couple definitions as we move on and start thinking about maybe slightly more complex angles or angle scenarios when we're dealing with angles outside of a triangle. First, the exterior angle of a polygon. Exterior obviously meaning outside. It's an angle formed by a side and an extension of an adjacent side. So I am going to use the picture I have down at the bottom of the screen, and I want to show you what an exterior angle is and what an exterior angle is not. So this is an exterior, or excuse me, that's a typical interior angle, angle X. This is not an exterior angle, okay? You might say, well, it's outside the triangle, it's outside the polygon, and therefore it's exterior, but it doesn't meet our definition of an exterior angle, which has an extension of an adjacent side. So let's look at a slightly different example. So we can talk about angle Y, and let's extend an adjacent side to angle Y. So this is the adjacent side to angle Y, and we're extending it right there. And this is our exterior angle, okay? So it has to be an angle between the polygon and an extension of another side of the polygon. All right, let me clean up that picture because we'll need it in a little bit later for something different, for something else. But that's what an exterior angle is. And then two remote interior angles, or excuse me, remote interior angles are the two non-adjacent interior angles to the exterior angle. So if we have this as angle X, for example, that's our exterior angle. These two angles, maybe Y and Z, are the two remote interior angles. And there's a pretty cool theorem that we won't prove right now, but I'll give it to you right now using exterior angles and remote interior angles. That the measure of angle X is equal to the sum of the measures of the two remote interior angles. So X is equal to Y plus Z. And I encourage you to think about where that comes from, why that has to be so. Maybe to push your thinking a little bit, maybe think about what two different ways of getting that green angle. Okay, there's a little clue for you right there. So let's use that to find some missing angles in triangles. So in this top triangle right here, we know that angle 1 is equal to 80 plus 18, is equal to the measure of the two remote interior angles. So the measure of angle 1 is equal to 98 degrees. Secondly, it looks like the exterior angle is 124 degrees, and that's going to be equal to 59 plus the measure of angle 2. So we could subtract 59 from both sides, and we get angle 2 is equal to 65 degrees. Okay, just using the fact that these two angles sum to that angle right there. Then in a quick real-world example, And you're seeing an airplane coming in for a landing at an airport here. Although it looks like the airplane's a little bit too high for the runway at this point if it wants to land. But anyway, we have a radar tower, and when radar is tracking an object, the reflection of signals off the ground can result in clutter, essentially resulting in a ghost image right here. So this, this radar tower is getting a view towards this plane right here, but it's also getting a ghost image of this, a ghost image of a ghost plane underground, okay, because of reflection off the ground right there. Anyway, we have a radar receiver at point A. Let me clean up my drawing a little bit. We have a plane coming in at point B, and we have reflection off the ground at point C, and we're really just looking for the measure of angle X. So I hope you can see right here that we have a triangle ABC, and we have one exterior angle has a measure of 80 degrees. We know one remote interior angle, and we're looking for the other remote interior angle. Okay, I'm going to show you two quick ways of doing this. One way is if you forget the exterior angle theorem, and then one way is using the exterior angle theorem. So let's do it twice. So first we'll use the exterior angle theorem that says that 80 degrees has to equal the sum of the two remote interior angles. We can subtract 30 from both sides and get x is equal to 50 degrees. If you happen to forget that angle though, we can find this angle right here and call it y. Okay, you should always remember that 80 plus y is 180 degrees. Those are linear pairs. That's a linear pair, supplementary angles. That means that y has a measure of 100 degrees. And then next we can remember, again, you should always remember that the angles in a triangle sum to 180. So we can say that 100 degrees plus 30 degrees plus x is our 180 degrees right there. And we can subtract from both sides, and we would also reinforce, get a check that x is equal to 50 degrees. So two ways of solving that problem. Remembering the exterior angle theorem is simpler, but if you're stuck, just remember linear pair and angles in a triangle sum to 180. So we did it, we got through it, and that's a great place to stop.